In this video, we will investigate Newton's law of cooling, which is just a specific scenario involving exponential growth or decay. So Newton's law of cooling is stated as following. The rate at which an object cools, or could warm, is proportional to the difference in the temperature between the object and the surrounding medium. So we're thinking maybe trying to model the temperature of maybe what a cold can of soda that you pull out of a refrigerator and set on a counter, or maybe it's some food item like a turkey you're placing in the oven and you're warming it up. So in order to model this, we need to introduce some notation. The typical thing to do is to let big T of little t represent the temperature of the object after t units of time, which will be made clear in the problem. T sub 1 we let represent the surrounding temperature, and T sub naught represent the initial temperature of the object. So the rate at which the object cools, so that would be d big T d little t, the rate of change of the temperature, is proportional. So remember, is proportional means equal up to a constant, proportional to the difference in the temperature of the object and the surrounding medium. So difference is subtracting. So the difference between the temperature of the object and the surrounding medium, with the initial value T of 0 equals T naught. So very similar to our previous example with exponential growth or decay, really the only difference coming with this T minus T1 on the right. In terms of what the solution will look like, it's very similar to our previous example, and once again we can kind of go through those steps that one might encounter in a differential equations course. So take that differential on the left here, the d big T over dt, and separate it out. So equivalently what we can do is think of having a dt on the left, dividing by t minus t1, and then multiplying both sides by d little t. And then, as previously, it looks as though this is missing those integral signs. So if we add those in, we have the natural log of t minus t1 on the left, and here I'm going to put absolute values, equals kt plus c on the right. And to get a formula for big T, we want to get it outside of that natural log. So if these two quantities are equal, the exponential evaluated at those quantities will be equal. So e to the natural log goes away. So we have t minus t1 equals, and I'm going to write this as e to the c, e to the kt. So we have big T as a function of little t is equal to initial temperature T1 plus a constant, I'll call it C1, e to the kt. And usually when I'm dealing with Newton's law of cooling, this is the formula I will immediately jump to. So it's the T of T is equal to the surrounding temperature plus CE to the KT. And note with Newton's law of cooling, once again, you really do need two pieces of data. One piece to solve for the constant C, the other piece to solve for the constant K. Let's investigate a very typical example. An object is taken from an oven at 350 degrees and left to cool in a room at 70 degrees. So right away we can note that this is a Newton's law of cooling. So we know that an object is taken from an oven at 350 degrees. So we're going to know that T of 0 equals 350 degrees, and it's left to cool in a room at 70 degrees. So that 70 degrees represents the temperature of the surrounding medium. So we have dt dt equals k times t minus 70. And if the temperature of the object fell to 250 degrees in 1 hour, so T of 1 equals 250, what will its temperature be 3 hours after it was removed from the oven? So from our previous slide, we saw that the formula for big T is going to be that initial, that surrounding temperature, so 70, plus a constant e to the kt. And then we need to use our two pieces of data to solve for the c and the k, and then we can answer the question that's been asked. So 350 is equal to t of 0, which is 70 plus c. So c, in this case, is equal to 280. Then we use our second piece of data, 250 equals t of 1, which is 70 plus c, so 280, e to the k times 1. So let's just do some quick algebra here. So 250 minus 70 is 180, divide it by 280. So we have 18 over 28, kind of losing those zeros, equals e to the k. So no, 18 over 28, we can simplify this a bit further, so that would be 9 over 14, so that our k value is the natural log of 9 over 14. So putting this all together, we now have our formula for the temperature of this object after t hours. So it will be that surrounding temperature, 70, plus our c value, 280, e to the kt. What we would like to know is what the temperature will be after 3 hours. So now is where we can just simply plug in 3 and evaluate in our calculator. So 70 plus 280 e to the natural log of 9 over 14 times 3. And if we plug this into a calculator, it's approximately 144.4 degrees.